Hi viewers. Welcome to this presentation on reactive power matching mechanism in power system. This sketch and the statement that power system frequency depends on load generation balance. This is known to power engineers. Precisely the statement may be power system frequency depends on active power injection and drawl in the system. Similarly, this sketch and the statement that bus voltage depends on reactive power injection and drawl at the bus may also be known. Here is small cluster of stations from grid system for study of relation and reaction of reactive power with voltage level at the bus. Station K is key station under study. Stations A, B, C, D and E are first-hand neighboring stations having direct line to K. Stations A, B, C, D and E are further connected to grid via one or more stations around. VB, VC, VD, V and VCO are the voltages at respective buses. Voltages VB and VD are higher than VCO. Voltages VC and V are lower than VCO. Power transfer on transmission line has following relations. 1. Active power transfer is proportional to angle difference between voltages at the ends. Active power flows from forward, higher angle to dragging, lower angle. 2. Reactive power transfer is proportional to voltage difference between the ends. Reactive power flows from higher voltage to lower voltage. Voltages VB and VD are higher than VK0. So reactive power QB and QD is flowing from respective station to K as per Formula 2. Total reactive power import at K is equal to KIMP is equal to K plus QB plus QD. Voltages VC and V are lower than VCO. So reactive power QC and K flowing from station K to respective stations. Total reactive power export from K is equal to QEXP is equal to QZ plus K. Net reactive power import at K is equal to KIMP, QEXP is equal to K plus QB plus QD, QZ plus K is equal to CO. CO is existing reactive power requirement at K, downward local demand. Now inductive load added at K. So reactive power requirement increase to QX. Reactive power available is CO and requirement is QX. Voltage start dropping due to shortage of reactive power support. Following changes starts along with voltage drop at K. Primary changes. Here is two-way corrections. 1. Increasing import. Voltage difference between A, B and D with respect to K is increasing. So reactive power import from A, B and D to K is increasing by K, delta QB and delta QD. Total increase of reactive power import is equal to K plus delta QB plus delta QD. Voltage difference between C and E to K is decreasing. So reactive power export from K to C and E is decreasing by delta QC and K. Total decrease of reactive power export is equal to delta QC plus K. Therefore net rise of reactive power at K is equal to K plus delta QB plus delta QD plus delta QC plus K. This means deficit of reactive power at K due to addition of inductive load is partly shared by all surrounding stations according to its capacity, either by exporting more reactive power to K or by reducing import from K. 2. Dropping demand. Reactive power required for inductive loads XL. Reactive power required is proportional to square of the bus voltage. Q is equal to V square divided by XL. Qx is equal to Wo square divided by XL, and Qn is equal to Vn square divided by XL. Qn divided by Qx is equal to Vn square divided by Wo square. Qn is equal to Vn divided by Wo square Qx. Vn is smaller than Wo. Qn is very small than Qx. The reactive power requirement at K dropped from Qx to Qn with voltage drop from Wo to Vn. So voltage drops to Vn till increasing reactive injection in match decreasing reactive power requirement Qn. Voltage var chart. System operating at O with net reactive import IO and reactive power requirement Rho at voltage Wo. Reactive power requirement increased to Rx due addition of inductive load. Voltage drop from Wo to Vn due to reactive power shortage. Reactive power net import increased from IO to N. Reactive power requirement dropped from Rx to Rn. Therefore, voltage is stable at Vn when Rn is equal to N. Foregoing discussion was about addition of inductive load at the bus K. Bus voltage was dropping. Reactive power requirement at K was dropping with voltage. Reactive power assistance receiving from all surrounding stations. Voltage stabilize at lower level when reduced reactive power requirement match with the increased net input. Similar phenomenon occurs in case of capacitor bank at station has tripped switched off or some line injecting reactive power to the station has tripped switched off. Shortage of reactive power on account of this is adjusted as above. There may be reverse process when reactive load has tripped switched off or capacitor bank line is taken in service. Excess reactive power cause voltage rise resulting in decreasing net import and rise in local reactive power requirements. Voltage stabilize at higher level when increased reactive power requirement match with the reduced reactive power supply. Secondary changes. Surrounding stations A, B, C, D and E will face reactive power shortage even though there is no local load rise. Reactive power shortage occurs because of assistance to K. Of course, shortage is small. Because part of total shortage at K is set off by drop in requirement due to drop of voltage. Only balance requirement is shared by all the stations. So shortage at each station is far less than original shortage at K. So all the stations A, B, C, D and E follows the same process as at K. All the stations have voltage drops and reactive power assistance from their surrounding station. So voltage drop is smaller and smaller in successive stages and may not be noticeable after second or third stage. Part of power map may be drawn on rubber sheet. Boundary of rubber sheet may be fixed on solid ring. Push the key station with point of ball pen pencil to simulate voltage deep due to reactive demand. Observe that key station downward move is maximum whereas surrounding stations have less. Station away from the key stations have very less and it is not noticeable at far stations. Summary. Frequency is grid base parameter. Frequency is same throughout the grid system. Variation of generation and/or load at any station anywhere in the grid reflects throughout the system as change in frequency. Therefore, counteraction of adjusting generation and/or load is feasible from any station anywhere in the grid with same effect. But voltage is node, bus, base parameter. So voltages may be different at different buses as per local reactive power balance at the node. Therefore, adjustment for reactive power balance is feasible at concerned node only. Adjustment for reactive power balance at adjoining station have very less effect at target node. Because alteration of reactive power injection requirement at other station is primarily affect locally and remaining is shared amongst all surrounding stations, whereas target station is one of them. Adjustment of reactive power at far station has no effect at target. Request: please like, subscribe and recommend others if found worthy. Viewers' comments welcome. Thank you, viewers. Bye until meet again in next episode.